All right, let's dive into chapter 4 of one of the most important books for developers, The Pragmatic Programmer. We're going to be talking about a mindset they call pragmatic paranoia. And look, it's not about being scared or negative. It's about being a pro, building software that's tough, reliable, and just works. So, first things first, let's get one thing straight. You can't write perfect software. I can't. The legends who built the internet couldn't. Nobody can. And you know what? That's totally okay. Accepting that we're all human and we all make mistakes is actually the very first step to writing truly great code, because once you admit that, you can start defending against your own errors. You've probably heard of defensive driving, right? You're on the road watching out for what the other guy might do wrong. A lot of coding is like that. We're checking for bad data or bugs in a library we're using. But pragmatic paranoia, that takes it to a whole new level. It means you don't just watch out for others' mistakes, you assume you're going to make them too. It's about building defenses against yourself. So, how do we actually do this? Well, we're going to break it down into 5 key ideas from the book. We'll talk about treating your code like a legal contract, why crashing your program is often the smartest move, and how to manage resources like a pro. We'll even cover why trying to predict the future is a trap. And then we'll wrap it all up into a simple toolkit you can start using like tomorrow. Okay, our first big idea, design by contract. I want you to stop thinking about your functions and classes as just chunks of code. Instead, think of them as 2 parties signing a legally binding agreement. It completely changes how you approach writing them. And this quote from Emerson just nails it. A software contract is all about plain dealing. It's about being crystal clear about what a piece of code needs to do its job and what it promises to deliver when it's done. No more guessing, no more ambiguity. So, what does this contract actually look like? Well, it has 3 main parts. First, you have preconditions. Imagine a function that calculates a square root. A precondition is that the number you give it must be positive. That's on the caller to get right. Then you have postconditions. The function promises, it guarantees that the number it gives back will also be positive. And finally, there are class invariants. Think of a shopping cart class. An invariant might be that the total price can never be negative. It's a rule that the class has to enforce, always. And what this does is create this beautiful, clear flow of responsibility. The code that calls your function does its job and meets the preconditions. Then your function can just focus on its logic, trusting that the inputs are good. In return, it makes sure the output is exactly what it promised. If something breaks, you know immediately which side violated the contract. It makes bugs so much easier to find. So the big takeaway here is this: write lazy code, and I mean that in the best possible way. Be really strict about the inputs you'll accept. Don't try to handle every weird edge case. And on the other side, promise as little as you can get away with in your return value. This keeps your functions small, simple, and way easier to test and maintain. All right, let's move on. What happens when a contract is broken? Well, the pragmatic answer might surprise you. It's simple. Crash the program. As the book says, dead programs tell no lies. Come on, we've all seen code like this. Maybe we've even written it. You've got one function, and it's wrapped in a dozen try-catch blocks trying to guess every single thing that could possibly go wrong. It's not just messy, it makes your code incredibly brittle. It's tightly coupled to the implementation details of whatever it's calling. The pragmatic fix is usually much cleaner. Just let it fail. Let the exception bubble up to a single, high-level handler that knows how to deal with it. You see this in web frameworks all the time. Some middleware catches any error and just sends back a generic 500 server error page. Your business logic stays clean and focused on its job. Now, this isn't just some random idea. This is the core philosophy behind some of the most reliable systems on the planet. Joe Armstrong, the guy who invented Erlang, a language famous for building telephone switches that literally never go down, he famously said this: "It's about accepting that failure will happen and building a system that can handle it gracefully." And here's the bottom line. A program that crashes immediately stops the damage. A crippled one? It might keep running, quietly corrupting your database, sending out wrong information, doing who knows what. Crashing early isn't a failure. It's a safety feature. Next up, let's talk about resources. You know, things like files, database connections, network sockets. The pragmatic programmer has a really simple rule for this. If you open it, you close it. You finish what you start. The classic mistake is having one part of your code open a file and then hoping that some other part of the code somewhere else remembers to close it. What happens if an error occurs in between? You get a resource leak. The fix is simple. The same routine that allocates the resource should be responsible for deallocating it. Modern languages give us great tools for this, like try finally blocks or using statements that guarantee the cleanup code always runs.
Now, what if you're juggling multiple resources? 2 simple rules. First, free them in the reverse order you got them. It's like stacking plates. Last one on is the first one off. Second, and this is a big one, if you need to acquire the same set of resources in multiple places, always acquire them in the exact same order. This is a classic trick to prevent deadlock, where 2 processes get stuck waiting on each other forever. This next principle has my favorite analogy in the whole book. Picture yourself driving down a dark country road at night. You can only see as far as your headlights shine. If you start driving faster than that, you're basically flying blind. Well, coding is exactly the same.
And that leads to this powerful idea. Your rate of feedback is your speed limit. How quickly can you know if your change worked? That's how fast you can safely go. Whether it's running a unit test, getting feedback from a user, or just trying something in the console, that's your headlight. You should never code further than you can see.
So how do you know if you're outrunning your headlights? Well, you can look for signs of what the book calls fortune telling. Are you trying to estimate a project that's 6 months out? Are you adding a bunch of complexity for a future feature that nobody has asked for yet? Are you guessing what your users will want next year? That's driving in the dark.
And this quote just sums it all up. Yeah, most of the time, the future is pretty predictable in the short term, but you can't bet your project on it. The pragmatic approach isn't to build for some imaginary future, it's to build code that's easy to change and replace today.
Okay, we've covered some pretty big ideas here, so let's boil it all down into a practical toolkit, a set of habits you can start building right now to bring this pragmatic paranoia into your own work.
Here it is, your toolkit. First, use contracts to make your code's boundaries clear. When things go wrong, crash, don't trash your data. Use assertions to check for things that should be literally impossible. Always finish what you start by balancing your resources. Keep your code simple by acting locally. And finally, always take small steps. Never make a decision you can't immediately get feedback on.
You know, embracing this mindset is one of the things that separates a junior developer from a true professional. It's not about being afraid to write code. It's about having the discipline to build software that can stand up to the real, messy world, and even our own mistakes.
So I'll leave you with a challenge. Think about the code you're working on right now. What's one assumption you're making? That a specific value will never be null, that a list always has at least one item. Find that assumption, and tomorrow, add a simple assertion to prove it. That's your first small step.